Welcome students to this lecture 3 of Elements of Discrete Mathematics. The main content in this lecture are the equivalence relation, partial order relation, chain, anti-chain and Hasse diagram. So first of all, we talk about equivalence relation. We have already given the definition of a relation in the lecture 2. So what is an equivalence relation? A relation R on a set A is said to be an equivalence relation if it satisfies the following properties. First is the reflexive. The relation R is reflexive. If X belongs to A, then the ordered pair XX belongs to R. In other words, the situation can be expressed like this. Uh, if we are taking here X, we are taking here X from A, then X related to X for all X belongs to A. And R is said to be symmetric if XY belongs to R, then YX belongs to R. Or in other words, you can say X related to Y implies Y related to X for all XY belongs to R. Third one, the transitive property. R is transitive. If xy belongs to R, yz belongs to R, then xz belongs to R. This situation can be put in another form that x related to R and y related to x related to y and y related to z, then x is related to z. Such a property is called transitive property, and if this property holds, then R is transitive. So if these three properties holds in a relation R, then we say that that relation is an equivalence relation. A very simple example from in real life, you can see if A is the set of all people in India, if xy belongs to A, then let us say that xy belongs to R if x and y, this look at this point, xy belongs to R if x and y have the same surnames, that is the last name, then R is an equivalence relation. So you can examine all the properties over here. The first one is the reflexive, symmetric, second and third is transitive. So you can see every person itself has the same surname. So X is related to X. Now, if we are considering two persons which are having the same surname, that means X has the same surname as Y, then definitely Y will have the same surname as that of X. So that this transitive symmetric property holds. Similarly, the transitive property. If a person X has the same surname as that of Y and Y has the same surname as that of Z, then definitely this X will have the same surname as that of Z. So transitive property also holds. So all these requirements are satisfied here. So we can say such a relation is an equivalence relation. Another very simple example is, suppose Z with a set of natural numbers and let a relation R is defined as x related to y if and only if x minus y is an even integer. Then R is an equivalence relation. This is a very simple example. Suppose first you are going to verify the reflexive property, and when will you say that this relation is reflexive? It can happen only when x is related to x, and according to the definition of the relation, when you will say that x is related to x, it can happen if and only if x minus x is an even integer. So let us look at x minus x. If you take x minus x, that will give you 0, and 0 is an even integer. So you can say x is related to x, that means x is reflexive. Now come to the symmetric property. You consider x related to y. What does it mean according to the definition over here again? X related to y means x minus y is an even integer. So we can write x minus y equal to an even integer. Take the minus sign common here, so it becomes minus of y minus x, and you take that minus sign of left hand side on right hand side. So you can say y minus x is minus of an even integer. But you know the negative of an even integer is again an even integer, because if you say 2 is even, then you will also say that minus 2 is also even. If this is even, that implies this is also even. That is the idea here. So because of that, you can say y minus x is an even integer, and hence you can say y is related to x. So what you have done here, you have considered x related to y and you have proved y related to x. Therefore, you can say that R is a symmetric relation. Then come to the transitive property. In the transitive property, you know x related to y and y related to z. These things are given. And you have to show that x is related to z. So how it can happen? It can happen only when if somehow you can show that x minus z is an even integer. So let us see. X related to y means this: x minus y is an even integer, and y related to z means y minus z is an even integer. This is equation star double star. If we add this equation star and double star, we get x minus y plus y minus z on left hand side, and in right hand side an even integer plus an even integer. So in left hand side this y goes with y, so x minus z equal to an even integer. Why? Because sum of two even integers is again an even integer. So therefore we can say x is related to z. So what you have proved here, that we have considered x related to y and y related to z, and finally we have established that x is related to z, as here you can see. So you can say R is transitive. Thus R is satisfying all the properties uh, that is required for a relation to be an equivalence relation, that is a reflexive property, symmetric property, and the transitive property. So we can say that R is an equivalence relation in this case. Next is the concept of divisibility and congruence. Let Z be the set of integers, and A belongs to Z is said to be divisible by B. B is non-zero, also belonging to Z, if there exists some integer q such that this A can be written as B into Q. If B divides A, if B divides A, the statement can be pronounced as B divides A, and mathematically it is denoted by this B, this vertical line, and A. It means B divides A, and mathematically its meaning is this, that A can be written as B into some integer. For example, I say 5 divides 10. Why? Because we can write here that 10 equal to 5 into some integer, and what is that some integer is 2. I can write it like that. So here I can say that 2 divides 10 as well as 5 divides 10. But if I say that 3 divides 10, this is not correct. Why? Because you cannot write 10 equal to 3 into some integer. There is no integer, so that their product equal to 10. If I write here 3 and another integer, I cannot find, so that the product will give you 10. So I can say this 3 does not divide 10. So this is the idea of divisibility. Keep in mind, I again repeat it, that an integer, non-zero integer or non-zero number divides this A if A can be written as B into some integer q. This is the idea. Now the congruence. What is the definition of congruence? For any two given integers A and B, if there exists a positive integer m such that you can write m divides A minus B. If m divides A minus B, then this type of situation is pronounced as A is congruent to B modulo M. and here B is called the residue of modulo M. Residue of modulo M. Now this situation can be written as like this. This M divides A minus B can be written like this. And it is pronounced as A is congruent to B modulo M. And it is equivalent to the divisibility relation, this one, M divides A minus B. For example, if we have two integers 2 and minus 7, there exists an integer 2 such that 2 divides 2 minus 7, because 2 divides 10, so this is correct. This is correct. And this can be written as 2 is congruent to minus 7 modulo 2. This can be written like this. This is correct. Now here if we have this thing, actually this is no, not 2, in fact it is 3. When this is 3, so it is 3. Now it becomes 10. So you can say this statement can be written like this, that is already there. But we cannot write 3 is congruent to minus 7 modulo 3, because in this case what is A is this, B is minus 7 and M is 3. So if I write M divides A minus B, is, it means that 3 divides 3 minus minus 7. That means 3 divides 10. This is incorrect. That is why we can say 3 does not divide 10. Therefore, this we cannot write that 3 is congruent to minus 7 modulo 3. So that is why this cross is being put here, that 3 is not congruent to minus 7 modulo 3. These are the properties of certain examples here, and even you can say these as properties, that if n is even, if and only if n is congruent to 0 modulo 2. Obviously n will be even if it is divisible by 2. So the situation is like that: 2 divides n minus 0. Equivalent mathematical way of writing this, if 2 is dividing some number completely, then definitely that number has to be an even number. Similarly, for the odd number, the remainder must be 1, so you can write 2 divides n minus 1, and 1 divides every number. So you can say a, since 1 divides a minus b, whatever a or b you can consider, so that is why a congruent to b mod 1, this statement is always true. This is one simple property. You can say that if A is A congruent to B mod M and A congruent to B mod D, then D divides M, and D and M are greater than 0. Both are positive numbers in integers. If you say D divides M, what does it mean? This M can be written as D into some integer K. Now you are given A is congruent to B mod M. What does it mean? M divides A minus B. And that means you can write A minus B is equal to M into some integer T. Now A minus B is equal to M into some integer T. But here you are given that M equal to dk. So you substitute the value of M here, and consequently this part becomes this dkt. A minus B dkt. Now here k is an integer, t is an integer, so k into t is again an integer, that is equal to r. So you, in place of this kt, you are writing r. Now what happens? What does it mean? It means you have obtained that a minus b equal to d into some integer r. D into some integer r. So you can say that D divides A minus B. D divides A minus B if it is happening. So it is correct, D divides A minus B, but when you write like this, so you can say A is congruent to B modulo D. So that is the thing which you wanted to establish, that if A is congruent to B mod M, then A will be congruent to B mod D, where D divides M. So we have established this. So very simple property. Next is congruence is an equivalence relation in Z. Suppose you are defining that R is the relation for any two elements A, B belongs to Z, such that A related to B if and only if A is congruent to B mod M. A is congruent to B mod M. So you want to show that this relation is an equivalence relation. First thing is the reflexivity. So reflexivity we check, we will show that A related to A. We will show that A related to A. So let us see, A related to A means, according to the definition, A must be congruent to A mod M. So let us check. A congruent to A mod M. It is correct. Why? Because M divides A minus A. Because if you have 0, then 0 can be divided by any number. So this is correct. When this is correct, this thing can be written like this. A is congruent to A mod M. And according to the definition, you can say A is related to A for all A belongs to Z. Therefore, R is reflexive. Next, we prove the symmetry. Let you consider A related to B. What does it mean? A is congruent to B mod M. But by definition, A is congruent to B mod M means M divides A minus B. That implies when M divides A minus B, then definitely M will also divide B minus A. For example, you say if I'm saying 2 divides 10, then definitely 2 also divides minus 10. So this is also correct. That is why we can write here, if M divides A minus B, then M will also divide B minus A, because minus, if you take minus common outside, so we'll get it. So that way you can say the meaning of this is B is congruent to A mod M. You have taken A congruent to B mod M and you have arrived at B is congruent to A mod M, and meaning of this is B is related to A in view of this definition. In view of this definition, A related to B if and only if A is congruent to B mod M. Means if you are given A related to B, its meaning is this. If you are given this thing, you can write it like this. So here B is congruent to A mod M. You can write it as B is related to A. So what happened here? You have considered A is related to B and you have proved B is related to A. Therefore, R is a symmetric relation. Similarly, we move on to the transitivity. You will consider A related to B and B related to C for all A, B, C belongs to Z. Now A and what you want to establish? You want to establish that A related to C. A related to C. That means ultimately you are going to find that A is congruent to C mod M. C mod M. You want to prove this thing. So let us see how it happens. You are given A related to B. What does it mean? That M divides A minus B. And if you are given B related to C, what does it mean? That M divides B minus C. Yes, when M divides A minus B and M divides B minus C, then this is the property of divisibility, that M will divide sum of those two. For example, I write here that 2 divides 4 and 2 divides 6. Then 2 will also divide 6 plus 4, that is 2 divides 10. So you can verify this thing. So when M divides A minus B, M divides B minus B, then definitely M will divide sum of these two. When you add these, B goes with B, B with B is cancelled out, and you'll get M divides A minus C. Now what does it mean? It means that A is congruent to C mod M, and that is what we wanted to establish, and hence you can say A is related to C. So here you can say A is related to C, and therefore R is transitive relation. So this relation R is satisfying the properties reflexivity, symmetry, and transitivity. So therefore this R is an equivalence relation, or we can say that a congruence relation is an equivalence relation. Now we have certain basic properties of the congruences. These can be proved also. So, but you can remember here, this A is congruent to B mod M and X is congruent to Y mod M. Then you can write the following things: AP plus QX equal to BP plus YQ congruent to this mod M. This property, then A and B and mod M, and here ACBC mod M, and A congruent to B mod M, C congruent to D mod M, then A plus C. If you are adding the things on left hand side, then you can write the residues on right hand side. So these are the important properties of the congruences. So next is the concept of a partial order set. What is a partially ordered set? And it is a in short, it is denoted by poset. A partially ordered set, generally written as poset. You can see a partially ordered set in which a binary relation x less than y is defined and which satisfies for all x y z the following conditions. One, the property 1 p1 is x less than equal to x. So this property is reflexivity. Then second property, x less than equal to y less than equal to x, then x equal to y. So this property is called anti-symmetry. And if x less than equal to y and y less than equal to z, then y less than equal to then x is less than equal to z. X is less than equal to z. This property is called transitivity. So if a relation is on a set, if on a set a relation is reflexive, antisymmetric, and transitive, if these three properties are satisfied, then we say that that is a partial ordered relation. And the set on which a partial ordered relation is defined is called a partially ordered set, is called a partially ordered set. So keep in mind, the very simple example regarding this. Let S be a non-empty set and PS be the power set of S. Power set means the set of all subsets of this set S. Let the relation less than equal to be defined as here. Note one thing, this less than equal to we are using as a general notation. It is not always the usual less than equal to. Usually you will say 2 is less than 3. You will say 2 less than equal to 2. So this is not the case that we are always talking about this less than equal to for the numbers only. Okay, so it is just a notation in this situation and it can take any meaning. For example, here you say A in a power set PS, A less than equal to B if you are defining the relation in this manner. A less than equal to B if and only if A is subset of B for all AB belongs to power set PS. If you are defining the relation in this manner, then PS less than equal to is a partially ordered set, means poset. So in order to establish that PS is a partially ordered set, you have to establish these three properties. First is the reflexive, second is antisymmetry, and third is the transitive property. So you see, every set is subset of itself for all A belong to PS. So you can say A less than equal to A because the meaning of less than equal to is A less than equal to B if and only if A is subset of B. What is meaning of this? If you are writing A subset of B, then it can be written as A less than equal to B. If you are writing A less than equal to B, then you can write it as A is subset of B. So that is the situation. So you know every set is subset of itself. Therefore, you can write A less than equal to A. Hence, this relation less than equal to is reflexive. The first property is done. Now, the second property, antisymmetry. if you are writing A less than equal to B and B less than equal to A. By definition of the relation less than equal to here, we can write A subset of B and B subset of A because of this B subset of A. Using 1 and 2, when A is subset of B and B is subset of A, so you can write A equal to B. Hence, less than equal to is the anti-symmetric relation. Third one, if you write A less than equal to B and B less than equal to C, what does it mean? A is subset of B and here B is subset of C. Now using 3 and 4, you can write A is subset of B is subset of C. So that means A is subset of C, or you can write A less than equal to C. Therefore, this less than equal to relation is a transitive relation. So three properties have been satisfied. These three properties have been satisfied here. So you can say the relation less than equal to, if defined in this manner on a power set of a set, becomes a partially ordered relation and PS becomes a partially ordered set. Next is the comparable element. Comparable element in a set. The element A and B of a partially ordered set. Suppose you are given this partially ordered set. This is the same less than equal to, but it is written in some different manner. The less than equal to, as we have talked earlier. If we have a partially ordered set S, then two elements are said to be comparable if either A less than equal to B or B less than equal to A. When elements A and B are such that neither A less than equal to B, neither this is true nor this is true, then these elements are called incomparable elements. These elements are called incomparable elements. For example, if we have the relation divisibility here, that means if you are defining, you have the set of positive integers, and here you are defining the relation A less than equal to B if and only if and only if A divides B. So this is the relation. We have given the same thing as an exercise in the last lecture, and you can see that this becomes a partially ordered relation. You can see that in this type of situation, we can find certain elements comparable and certain elements are not comparable in such a set. Let us see these two elements. 3 and 9 are comparable. Why? Because 3 divides 9, it is true. When 3 divides 9, then according to this relation, we can write 3 is less than equal to 9. Therefore, 3 and 9 are comparable. Now let us look at another pair of elements. 5 and 7 are not comparable. These can be comparable if I can write 5 less than equal to 7 or 7 less than equal to 5. But according to definition of relation in this case, if I write 5 less than equal to 7, then the meaning of this is 5 divides 7. So this is not true. Now if I write 7 less than equal to 5, the meaning of this will be 7 divides 5. Again, this is not true. So both the situations are not valid in view of this relation. Therefore, 5 is not less than equal to 7. 7 is not less than equal to 5. Therefore, 5 and 7 are not comparable elements. So that is the solution given here. The adjective in a partial ordered set, the adjective partial is given because of the partial ordering. Because of partial ordering. Since in this situation here, we have observed that certain elements are comparable and certain elements are not comparable. That means order of all the elements is not possible. That is why such sets are called partial ordered set. But if we have sets in which all the elements are comparable, every pair of two elements are comparable, then such sets are called the totally ordered sets, and the ordering on that case are called total ordering. So next is the similar definition, totally ordered set. If S less than equal to is a partially ordered set, every two elements of S are comparable, then S is called totally ordered set or linearly ordered set. And this relation less than equal to is called a total order or the linear order. Total order or the linear order. A totally ordered set is also called a chain. Keep in your mind the term chain. A totally ordered set or a chain, these are the same things. So these are the examples. A partially ordered set Z less than equal to is totally ordered because A less than equal to B or B less than equal to A whenever A and B are integers. In this case, you have to define A less than equal to B if and only if A less than equal to B in usual sense. Usual sense of less than equal to, you know, as I have already explained, 2 less than equal to 2 or 3 less than 4, like this. We can also write 3 less than equal to 4. So one of these must hold either equal to or less. So we can write like this. So in usual sense, if we say Z will be the set of integers is definitely a totally ordered set, because you take any two integers, one will be smaller, one will be greater, or two integers may be equal here. So this partial ordered set Z of positive integers is not totally ordered because we have explained there are some certain incomparable elements. Next we come to concept of Hasse diagrams. So what are Hasse diagrams? In the last lectures, I have explained that every relation can be written as, can be represented as a graph, as a directed graph. Directed graph means in which the edges have directions. So every relation has a graphical representation. But in the graphical representation, if certain things are omitted, certain edges are omitted in view of the properties of partial ordering, then the final graph obtained in this manner is called a Hasse diagram. So what is the definition? Many edges, how this problem occurs, many edges in a directed graph of a finite partially ordered set do not have to be shown because they must be present. Means if we omit certain edges, even then their presence is obvious. So the such simplified representation, the simplified graphical representation of a relation is called a Hasse diagram. Consider the directed graph for the partial ordering that A related to B. A comma B means you can also write A related to B if and only if A less than equal to B on this set 1, 2, 3, 4, and that is shown in the figure 1a, this one. When we are defining set is here and the relation is this, that means in this case we will define the relation like this: A if and only if A less than equal to B in usual sense. So definitely you can represent in this case, if you write the pairs, the relation here, set S is this one. So I say set S is here 1, 2, 3, 4. Okay. So S cross S in this situation, S cross S in this situation give you the 16 element, 1 with 1, 1 with 2, 1 with 3, 1 with 4, and so on. In the same manner, you will say 2 with 1, 2 with 2, 2, 3, 2, 4. All the pairs we have to write 3, 1, 3, 2, 3, 3, 3, 4. Then 4, 1, 4, 2, 4, 3, and 4, 4. So out of these we see which one must be in the relation, because the relation is here that a the pair AB can be written A less than equal to B if and only if this, or I can say A comma B belongs to R if and only if A less than equal to B in usual sense. So both are the same representation, meaning of both is same. So in the relation only those pairs will be there in which the first element is less than or equal to the second. So in the relation R, certain elements will be omitted here from the Cartesian product I say. So certain elements I can cross which will not be present in the relation. For example, here in this case 1 is less than equal to 1, it is okay, this is okay. 1 is less than 3, this is okay. 2 is not less than equal to 1, so it will not be in the relation. Rest of the things will be in relation. This will not be in relation because first element is not smaller than the second. This will not hold. In this case this will not hold, this will not be there, this will not be there. So remaining elements will be present in the relation. For example, 1 is related to 1, so there is an edge from 1 to 1, there is an edge from 1 to 1, then 1 to 2, this direction, 1 to 2 arrow, then we are having 1 to 3, 1 to 1 to 3 is this one, then we are having 1 to 4, 1 to 4, 1 to 4 is this one, we are having this one. Similarly 2 to 2, when 2 is related to means this is a loop, 1 to 2 to 2. Similarly 3 to 3 we have the loop, 3 to 3, 4 to 4 all are there, so these are the loops here. And then we are having 2 to 3, 2 to 3 is this line, similarly 3 to 4. So if you similarly if you look at in all these pairs, then you can get this type of graphical representation. Now because this relation is a partial ordering, it is reflexive, it is a directed graph, have loops at all vertices. Consequently we do not have to show these loops because they must be present, because this is the simplified representation of a relation. And definitely it is a partial ordered relation, it is a partial order relation, so it has to be reflexive. When it is reflexive, then every element must be related to itself. That means loops are already supposed to be present here, so even if you don't represent the loops, they will be considered over here, so you omit the representation of loops, so consequently you get this form. Now in figure 1b, loops are not shown because a partial ordering is transitive. We even do not have to show those edges because of transitivity. For example, in the figure 1c, the edges 1 3, 1 4 and 2 4 are not shown. 1 3, 1 2 3, this is not shown because it is obvious, because in a partial ordered set transitivity holds, one related to 2 and 2 related to 3, then definitely one will be related to 3, so no need to represent this line, no need to represent this part, so you can omit it. Similarly 2 related to 3 and 3 related to 4, so 2 will definitely be related to 4 because of transitive property, so no need to represent this line, you can omit this one also. Exactly in the same manner, 1 related to 2, 2 related to 3, 3 related to 4. So 1 will be related to 4 automatically due to the transitive property. So no need to show this. So remove these three curved lines. So finally we get the simplified representation. So this is the simplified directed representation of the, not the directed one. Now no need to write the direction because when 2 at the upper level, and that means 1 will be less than 2, 2 less than 4, and 2 less than 3 and 3 less than equal to 4. So this representation is called the Hasse diagram, and this is Hasse diagram for this partial ordered set A B such that A less than equal to B in the set of these four integers. So this is about Hasse diagram. Similarly, if you look at this Hasse diagram representing the partial ordering A B such that A divides B on this set. So here you will see this diagram also, because you can see how many pairs will be there. Suppose you say that this set is S, this set is S, then S cross S will consist of 3, 3, 6, 7, means 49 elements. In the set there will be 49 ordered pairs. But out of those 49 ordered pairs, in the relation R, you have to consider only those pairs such that the first element divides the second element. Only those pairs will be considered. For example, one can be paired with all of these, because 1 divide 1, 1 divide 2, 1 divide 3. So definitely loops will be there at all the vertices. Loops will be there at all vertices, because 1 divides 1, so you can write 1 related to 1. 2 divides 2, loop is there, loop is there. At every vertex there will be loop. And one will be related to all of these. One related to 1, one related to 2, the arrow is here, one related to 3, one related to 4, one related to 4 is here, one related to 5, 6, this line, etc, etc. Similarly, you can relate 2 with 1. 2 with 1 cannot be related because 2 does not divide 1. In the same manner, 2 does not divide 3, 2 does not, but 2 divides 4. So there is a line between 2 to 4, but there will not be line 2 to 1, the direct line. There is no line from 2 to 3 because 2 does not divide 3. In this manner, construct this type of directed graph, and from this directed graph you can see, if you omit the loops you get this representation. If you omit the transitive properties, the edges due to transitive property, we get the final representation in this form. So this is the Hasse diagram for that partial ordered set. So this is about this lecture, and most of the things are taken from these books. Thank you.